Welcome back, everybody. Welcome to Math 1314, More on Math. Today we're going to discuss Chapter 5, Section 2, which is Exponential Functions and their Graphs. That's our objectives. We're going to discuss exponential functions and their graphs. What are they? What do they look like? What do they do? And then we're going to solve a problem using exponentials. All right. In the past, we talked about, whenever we talk about exponents, we always looked at something like this. 2 to the x to the power something, where x was the base and some number was the exponent. That was then. Now we're going to discuss exponential functions. When we talk about exponential functions, x changes position. X is now the exponent. And we have some number as the base. All right. Because x is the exponent, it was the number that we have on the bottom. A has certain restrictions. A has to be positive, has to be greater than 0, and A itself cannot equal 1. And here's the reason why. A has to be positive. If A was negative, let's say we had negative 2 to the power x. So if we had negative 2 to the power 2, that equals positive 4. If we had negative 2 to the power 3, it would give us negative 8. So whenever the exponent is even, we'd have a positive answer. Whenever the exponent is odd, we have a negative answer. So the graph would just be an oscillating, a snake-type graph. So that's the reason we have to limit ourselves strictly to positive numbers, so we always have the same type of numbers. A cannot equal 1 because anything to the power 1 is 1. That would just be a horizontal graph at 1. That would be pretty boring. All right, let's look at this. Because A has to be positive and it cannot equal 1, and if we had a number line, it has to be positive and it can't equal 1. So we have two sets of numbers that we could look at. We have A is greater than 1. That's this part. And A is between 0 and 1. Interesting thing happens with both of these. So, remember, we're looking at this equation. Well, let's pick a number. Let's say A is 2. For this example, I'm going to show you, all the graphs are going to look the same, but I'm picking number 2. Well, not the same, they have similar structures. So since A, the base is positive, 2, raised to any power is always going to be positive, so all of our answers will always be in the positive range. Our range is from 0 to infinity. All right, so let's look at this. At 0, anything to the power 0 is 1. So we have a y-intercept at 1. And that's always going to be the case. For no matter what A is, it's at the 0 power it's 1. So the y-intercept is always going to be 1 unless we have a transformation. So let's create a table. Let's pick some numbers. Say negative 2, negative 1, 0, 1, and 2. Well, at 0, when x is 0, we know it equals 1. That's that. x is negative 2. If x is negative 2, remember, a negative exponent doesn't mean the answer is negative. A negative exponent simply means that number goes on the bottom. So 1 over 2 squared is 4, so it's 1 over 4, 1/4. So it's down there, approximately down there. All right, let's do the same thing with negative 1. 2 to the power negative 1 is 1 over 2, which is a half. Okay, we notice something that's happening there is it's increasing. When x is 1, 2 to the power 1 is 2. 2 to the power 2, 2 squared is 4. So at 1, it's 2. At 2, it's 4. So the graph has that basic shape. No matter what the base is, as long as it's greater than 1, it'll have that basic shape. It'll never cross the x-axis because this number can never be 0. The only way it can equal 0 is if a is 0. And it can't be 0. We pick number 2. So we have a horizontal asymptote at 0. Actually, the x-axis. All right. Now let's look what happens if we have a decimal or a fraction. In order for a to be between 0 and 1, it has to be a fraction or a decimal. Let's create a table here. So we have x and y. It's, we can use the same number, same equation, 2 to the power x. And this time, let's use the same number. Oh no, a has to be different now. A is going to be 1/2. If a is between, so it has to be a fraction. So at negative 2, negative 1, 0, 1, 2. Remembering, whenever you have a negative exponent to a fraction, what that negative does is it flips the fraction. So 1/2 becomes 2, the negative drops, so 2 squared is 4. So at negative 2, it's 4. At negative 1, that negative flips the fraction, so 2 to the power 1 is 2. Anything to the power 0 is 1. 1/2 to the power 1 is 1/2. 1/2 squared, that distributes, so 1 squared is 1. 2 squared is 4, so it's 1/4. So at 1 it's 2. At 0, 1/2, 1/4. So you see what happens here is the graph flips. It flips across the y-axis. So when it's between 0 and 1, it's a decreasing function. If it's greater than 1, it's an increasing function. All right, so that's the first thing we have to notice. That'll give us an idea what the graph's supposed to look like when we get to do problems. If it's a fraction or a decimal, it's a decreasing function. If it's an integer greater than 1, then it's going to increase. All right, let's look at the properties. The properties of an exponent. Properties of exponential functions. So we have, here's the function, a to the power x, where remember, a cannot equal 1, and a has to be positive. The first property, remember our graphs, the function is continuous. In other words, no breaks. Once you start at one end of the graph, you can keep on drawing the whole thing without ever lifting your pen. It's 1 to 1. In other words, it passes the horizontal line test. Since it's 1 to 1, it has an inverse. All right. The domain, all real numbers, from negative infinity to positive, all real numbers. The range is always going to be above the x-axis. So it's from 0 to infinity. It's an increasing function when a is greater than 0. It's a decreasing function if a is between 0 and 1. The horizontal asymptote is equal to 0, the x-axis. And the most important one is the y-intercept is equal to 1. It's at the point 0, 1. Unless, of course, there's a transformation, which we're going to look at in a second. So those are properties of exponential functions. So let's look at some examples of some transformations, what it looks like and how we do it. We're going to use the basic function 2 to the power x. Again, you can use any base you want to. It's going to have the same shape. Remember, it goes through 1 and it looks like this. So what if we had this equation? 2 to the power x minus 2. Because this has, we can't do an exponent until we fix this number, figure out this number. Once we plug in x, we subtract 2, then we do the exponent. So that's a horizontal shift. Anytime you affect the x first before the function, then it's a horizontal shift. And remember, it's always opposite. So if you don't remember how to do that, set your x function to 0 and solve for x. There's your new origin. When x is 2. So we know our graph remember at 1 it's 2 At 2, it's 4. So our origin shifts to the right 2 spaces. So now we have a new origin. There's a new origin. Again, so our graph used to cross at 1 here. Now it crosses at 1 there. At 1, it's 2. At 2, it's 4. It's just that it's shifted now to the right. There's our new graph. It just shifts to the right. What if our function looked like this? X is not affected. The base doesn't change. All we have is this. It's outside the function. The function is 2 to the power x. So this is a vertical shift because it only affects the y values. It goes down 4. Remember, all a transformation does is it shifts the origin. So the origin of the original graph is there. It shifts it down. 1, 2, 3, 4. It's now at negative 4. There's our new origin. From this line, the graph still crosses from the one up above the x-axis at 1. From here, you go up 2, 1, 2. From the 2, you go up 4, 1, 2, 3, 4. And then same thing. So there's our graph. Only thing you do is just shift it down. What if we had something like this? This has all sorts of transformations. So here's the function. The base is a fraction. So we know that the graph's going to look something like this because it's a fraction. It's negative. Whenever the function turns negative, it flips over the x-axis. So our graph looks like this now. So I'll do it step by step. 0.5x. Because it's a fraction, this is between 0 and 1, so it's a decreasing function. It's negative. So it flips across the x-axis. And this number is our vertical shift. It's positive, so it goes up 5 spaces. Remember, our origin used to be at 0, 0. It shifts up. 1, 2, 3, 4, 5. There's 5. So we have a new origin here. Our graph origin shifts there. So now we're going to draw our graph there. Remember, because up here it crossed at 1 above it, when we flip it over, it crosses at 1 below it. At 1 back, you go 2 down. At 2 back, you go 4 down. So that's here. Remember, it's a decreasing function, so it looks like this. in this case, but it's increasing now. But there's the graph. That's how you transform them. All right. Let's look at an application. The most common use of exponential functions are in business and in science and engineering. The most important one that you're going to have to learn when you start being a consumer, buying houses and cars and whatever else, is this formula. This is called the compound interest formula. Where A is the annuity. In other words, that means the amount owed. The annuity is what is it worth at that time. P is the principal. That's the amount borrowed. So if you're financing a car, it's the price of the car. If you're financing a house, it's the price of the house. That's a P, principal. That's that one. R is the rate of interest. It's given to you in a percent. You have to convert it to a decimal to use this formula. It's pretty easy. So if it's 20%, just move the decimal 2 to the left. If it's 5%, the decimal's right behind it, move it 2 to the left. So it's 0.05. N is the number of times a year interest is calculated or processed. So if you have something that says annually, N is 1. If it's semi-annually, that's 2, because it happens twice a year. So how many times a year? If it's monthly, it's 12, because there are 12 months in a year. Weekly, there are 52 weeks in a year. Daily, 364. Don't count Christmas. Because of 365 days, but you don't count Christmas. All right, so again, the more often you calculate, the bigger the number. And T is the time in years. How many years are you going to borrow the money? For a car, it's usually 5 years. For a house, it's usually 30 years. The longer you finance something, the more expensive it becomes. The less you finance it for a less period of time, the cheaper it is. So let's see, you want to buy a car, $10,000. You're going to buy it at 10%. For cars, sometimes it is that high. It may be higher if depending on your credit rating. It's going to be compounded annually. And you're going to do it for 5 years. So you just plug the values in. 1 plus, remember, 10% is 0.10, so 0.1. Let's make it biannually. Oh, monthly. Let's make it monthly. So 0.1 over 12. Here it's 12 times 5. So 10,000. And you have, let me get your calculator here. But these you will need a calculator on. So the first thing you have to do is 1 plus 0.1 divided by 12 equals 0.00833333. 12 times 5 is 60. Order of operations, you have to do inside, so it's 1.0083. Then you have to take this, raise it to the 60th power. That gives us 1.6453. Now, on your calculators, when you want to do this, there's a button that looks like this. This number is the X, this number is the Y. So when you have this number, press this key, and it's going to ask you for the exponent. Then you hit enter, you'll get this. Now, when it says 10,000, each zero in the equation, that's one decimal place to the right. So 1, 2, 3, 4. So your $10,000 car actually cost you $16,000 after 5 years. This is the amount of interest that you accrued. Over half of the car's price went to interest. So that's why people do a down payment whenever they pay for cars, because make that smaller, make it a little easier. Also, the interest rate. The better your credit rating, the lower the interest rates will be. Because it sounds backwards. If you have bad credit rating, you have to pay higher interest. That's because it's a gamble they take to give you money. If you have a bad credit rating, that means you're not too sure about how comfortable you are with money. Will they get their money back? So again, it's very important to have a good credit rating. And the number of years. If you only did it for, instead of 5 years, you did it for 3 years, that number would be smaller. It'd be 36 instead of 60. So that means this number would be smaller, which makes the whole thing smaller. Let me show you. Let me see. So if instead of 3 years, if I used, instead of 5 years, if I used 3 years, so I have 10,000 times, where's my parentheses? No, it's 1.0083 to the power 36. For 5 years, it was 16,453. For 3 years, it would be 13,465.78. Divide that, because in 3 years, 36 months, so divide that by 36. Your payments will be $374.05 per month. So take the number of months, the amount you owe, divide by 36 equals that value. Let's see how much that's 16,453 divided by 60, because that's 60 months in your 274.22. Well, yeah, the reason it's lower is because you have more years to pay it off. So you have lower amount to pay each month, $100. But that's what I said. If you owe this, if your payments this, try to make your payments twice a month, or try to put some extra money down, because it'll make it go down much faster. All right, so that's an example of application of exponential functions. A gentleman named by the in the 1700s, in 1790, 1740, 1790, 1740-ish, a gentleman by the name of Leonard Euler, very famous man in mathematics world. He decided, well, let's look at this equation here. What if I want to borrow $1? That's my P. For 1 year. That's my time. At 100% interest, or percent rate. So he said that P is 1, so there's no, R is 1, and T is 1. So his equation broke down to this. I call it E for Euler. And as n goes to infinity, he noticed that this number, E, this equation, approached a specific value. 2.718, 28182824, it keeps on going. We call that Euler's constant. Or Euler's number. So whenever you see the letter E in an equation, that's what it's all about. All right? So let's look at some examples here of what it looks like. Because it's a constant, we can have an exponential of it. because the base satisfies the condition. It's positive, it's 2.7. It's greater than 1, it's 2.7. So the graph crosses the y-axis at 1. At 1, it's 2.7. At 2, it's a little bit bigger. So it grows a little bit faster than our other equation, but it has the same shape. And since it is 1-to-1, it also has an inverse. And that's what we'll cover in a little bit. So the transformations exist the same way as we did earlier. X plus 3 since this happens to x, it's a horizontal shift, 3 to the left. So my new origin is there. So the origin shifts 3 spaces to the left. Remember, it's always the opposite. It crosses at 1, and it grows. One minus e to the power negative 2x. Okay, see what happens here. The first thing we see, the basic shape of e to the x is like this. We have an exponent. So it grows twice as fast, so it's more steep. It's negative, so it rotates around the y-axis. Because remember, anytime you change the sign of x, it rotates about the y-axis. The e is negative, so it flips across the x-axis. And then there's a 1 in front of it. So it's a vertical shift. It goes up 1. So it goes up 1. No, this is not a negative. So there's your new origin. It still intercepts 1 away from the origin, so here's my intercept, and the graph looks the same. So that's it for section 2. Good luck.